Can you hear me? Okay, great. Well, thank you for the introduction and the invitation. It's great to be in Korea for the first time. And today I'll be telling you about some work I've been doing over the past couple of years on sort of stuff you can do with higher form symmetries. Yeah. I should say that this is work that's being done with several people. First and foremost, Oliver Hart, who's a postdoc at Boulder, currently on the market. Then Charles Stahl, my former student, now at Stanford. David Stephen, a former postdoc, now at Quantinuum. And Alexei Khodoroshkov, who's a graduate student at BU. Okay, so no, to set the scene, what happened here? Yeah. To set the scene, now ultimately, like, one of the things I'm very interested in is non-equilibrium physics, and non like equilibrium systems are by now fairly well understood. We don't understand everything, but we at least have a sort of basic understanding and map of the possibilities. In contrast, non-equilibrium systems really are here there be dragons territory. So in the non-equilibrium setting, we can have stuff like spontaneous symmetry breaking in one dimension at high temperatures, or topological order without a bulk gap, the sorts of things that we usually think can't happen, but it can happen in the non-equilibrium setting. And okay, the one issue with non-equilibrium is in what way are you being non-equilibrium? Yeah, equilibrium systems are equilibrium systems, but you could be non-equilibrium in any number of different ways. And one particularly dramatic way in which you could be non-equilibrium is you set up a system in some specific initial condition and you wait a very long time and it never goes to equilibrium under its own dynamics. Yeah. And so that's the sort of setting in which I'm really interested in asking questions about non-equilibrium physics, systems that don't equilibrate under their own dynamics. And to be especially interesting, I want the systems to not equilibrate under their own dynamics, even when prepared at a non-zero energy density. So what are ways in which this could happen? Well, sort of historically known ways, of course, there's integrability. Recently, there's been discussion of scars. Common to both integrability and quantum scars is that these are essentially fine-tuned phenomena. I mean, this could be a true statement about some particular Hamiltonian, but you perturb that Hamiltonian infinitesimally, and it's entirely possible that in the thermodynamic limit, the special structure goes away, and it goes away on a time scale which is only some low-order polynomial in perturbation strength. Typically, it may just be a time scale set by something called Fermi's golden rule. Yeah. So these are known ways to avoid equilibration, but they're not robust. Then there's many-body localization, which is associated to systems with strong quenched disorder. Very interesting topic, not the topic of today's talk. Yeah. I'm interested in ways to get ergodicity breaking which are not integrability, scars, or many-body localization. And is there anything else? And if you'd asked me that, I guess 7 years ago, I would have said we don't know of anything else. But now we do. Yeah, there are alternative routes to non-equilibrium physics, which are not just these three. So the first of those is essentially the interplay of symmetries. So we realized about 5 years ago that the interplay of finitely many symmetries can lead to robust ergodicity breaking and dynamical phenomena. And we first discovered this when we were looking at systems with dipole conservation. And of course, there were lots of talks about dipole conservation yesterday. Yeah. Now, in terms of how this comes about, this is the phenomenon that is now known as either Hilbert space shattering or Hilbert space fragmentation. Both these terms mean exactly the same thing. They can be viewed as interchangeable. And the setting here for this original discovery of sort of Hilbert space shattering or fragmentation in dipole conserving models was you have a system with a finite number of symmetries which are present essentially exactly, and the dynamics is generated by operators with compact support in real space. Yeah? So we have symmetries and we have strict locality. If you don't have strict locality, then you get sort of different story. This is the story that's known as fracton hydrodynamics. Again, lovely topic, not the topic of today's talk, but we had some talks on sort of inspired by fracton hydrodynamics last year. But this is sort of background to what I'm going to talk about. So fracton hydrodynamics is great, but fractal hydrodynamics, ultimately the system does go to equilibrium. Yeah? It's just that the approach to equilibrium is slower than ordinary diffusion. It's given by some kind of subdiffusive hydrodynamic universality class. So that's great, but I actually want to break equilibrium. I don't want my system to go to equilibrium even subdiffusively. And I want to do better than Hilbert space shattering fragmentation in the charged dipole models, in that there we really needed spatial locality, and I don't want to rely on spatial locality. So my motivating question for this talk is, can we get ergodicity breaking, meaning system doesn't go to equilibrium even at very long times, and can we get that without demanding either exact symmetries or strict spatial locality? And the answer is yes. That's what today's talk will be about. And the way that I'll structure the talk will be the following. I'll start by introducing an explicit model, which introduces many of the key ideas. And this model will also explain how sort of higher form symmetry can be of use to understanding this sort of dynamics. It's very physical. It's based on a sort of generalized Rydberg problem. Then I'll introduce a very broad set of generalizations and abstractions of these ideas. I should say that the first two parts of my talk will be essentially pre-thermal, and what I mean by this is that there will be some fine-tuned Hamiltonians which never equilibrate, even to infinite times. And if I perturb about those fine-tuned Hamiltonians, then one can show that there's no equilibration out to a time scale which is super polynomial in the perturbation strength. So if you take the perturbation strength to 0, then the time scale diverges faster than any polynomial function of perturbation strength, and typically it'll be exponential in perturbation strength. Yeah. So if there is relaxation, it's not coming from any finite order in perturbation theory. So in that sense, these models are much more robust than, say, integrability or quantum scars, but this still begs the question of, well, okay, exponential in perturbation strength could be very long. Practically, it may be indistinguishable from infinity, but as a matter of principle, it's still finite. So can you get timescales that are truly infinite in this setting? And in the final part of my talk, I'll talk about how the notion of sort of exact emergent higher form symmetries may even give us a route to truly infinite timescales, not really distinguishable pragmatically from the first part of my talk, but maybe sort of distinct as a matter of principle. Okay, so let's start. Everything should be made as simple as possible, and I think the simplest example I know of to illustrate these ideas is what we call the CZP model. So the setting here is we're working in two space dimensions on a square lattice, and we place spin 1/2 variables, or qubits if you prefer, on every vertex of the square lattice. And the Hamiltonian takes the following form: H0 plus V, where V is anything k local. Yeah? And by k local, I mean it's a sum of terms where each term acts on finitely many degrees of freedom, but it could be, xi, yj, zk, where I, j, k are freely chosen in real space. Yeah? So there is no requirement of spatial locality for V. It's only local in the quantum information sense, not in the sense of geometric locality. Yeah? So I'm allowed to perturb with sort of non-local perturbations, and I assert that for arbitrary V, local, non-local, we don't care, this system will break ergodicity. So this is a very dramatic claim, and obviously much is going to turn on what H0 is, and what H0 is doing is it's enforcing a sort of generalized Rydberg constraint. So H0 has the following form: it's sum over all plaquettes, and on every plaquette we have this operator control Z plaquette. If you're from a quantum information background, then you can think of CZP as being the product of control Z gates around the 4 links of an elementary plaquette. If you're from a sort of lattice Hamiltonians background, then you can think of CZP as being the following operator. So you have vertices I, J, K, L, and you have 2 spin interactions on the diagonal and 4 spin interactions around the plaquette. Yeah? It's just some operator. It's an operator which squares to 1, so it has eigenvalues plus or minus 1. And if you work in the Z basis of Z basis product states, then if you have an odd number of neighboring ones around a plaquette, then this operator has eigenvalue minus 1, and otherwise it has eigenvalue plus 1. Yeah? And if you make J large and positive, then this operator wants sort of every plaquette to be happy, which means you don't ever have an odd number of neighboring ones around any plaquette. And that's, you can view as essentially a constraint. Anytime you violate that constraint, you pay a large energy penalty of order J. Yeah? So how big is the constraint satisfying subspace? Well, it's relatively straightforward. You can estimate it. You can also get an exact count. I won't necessarily go through it, except to say that the size of the constraint satisfying Hilbert space is roughly this large, this large. And this number is exponential in system volume. Yeah, we're in 2 dimensions, so L squared is system volume. So the size of the constraint satisfying Hilbert space is exponential in system volume, meaning if you take a logarithm of this constraint satisfying Hilbert space, that's extensive. Yeah. So the constraint satisfying Hilbert space is large enough to be able to accommodate a non-zero entropy density. Yeah, it's an honest 2-dimensional many-body Hilbert space, and so it's sensible to talk about thermalization or lack thereof in this constraint satisfying Hilbert space. By the way, if you have questions at any point, please put up your hand and ask as we go along. Okay. Now, in order to actually understand the physics, it's convenient to go to a dual representation. So when I wrote down this Hamiltonian, the CZP term actually has 2 Ising symmetries. So this Hamiltonian is formulated on the square lattice. The square lattice is bipartite. There's an odd sublattice and an even sublattice. And if you do global Ising spin flip, z2 minus z, on either the odd or the even sublattice, that is a symmetry operation. So there's 2 Ising symmetries, one for the odd and even sublattice respectively, and you can introduce one set of domain walls for the odd sublattice, another set of domain walls for the even sublattice, and these are just the domain walls of the Ising symmetry on the odd and even sublattice respectively. And for clarity of visualization, I will denote them as red and blue. Yeah? And on any given plaquette, you could have 0 domain walls, 1 red domain wall, 1 blue domain wall, or both a red and a blue domain wall. And the constraint that we have been enforcing amounts to saying that you cannot have this situation, because if you have both a red and a blue domain wall on the same plaquette, then you have an odd number of neighboring ones around that elementary plaquette, and that is a constraint violation. Yeah? So if we look at our constraint satisfying space, the constraint satisfying space is a set of states which consists of 2 species of closed loops. Closed loops because domain walls always form closed loops. Yeah? So there's 2 species of closed loops, red and blue, with the additional constraint that red and blue closed loops cannot intersect. Yeah? And then the dynamics just consists of fluctuations of these closed loops. So loops can pop in and out of vacuum, they can fluctuate, you can do anything you like, they can fluctuate freely, subject to the constraint that red loops and blue loops cannot intersect. Yeah? So we have a Hilbert space, which is 2 species of non-intersecting loops, and we have dynamics, which is local fluctuations of 2 species of loops subject to this non-intersection constraint. And now I invite you to consider states of the following form. Leo.
Satisfy any
Every constraint violation costs energy J, which is large.
But non-violating, they're all equivalent. They're all equivalent energy.
Right.
Before you start hopping around.
Before you add any perturbation term V, they're all degenerate. Yes. Okay. Once you add a perturbation term V, they're not degenerate anymore.
Okay. These are solutions of H0 only.
These are, yeah. Okay. These are all zero energy eigensolutions of H0.
Thank you.
Yeah. Okay, so now I invite you to consider the following sort of configuration. So what this is meant to be is a dense packing of loops, alternating red, blue, red, blue, red, blue, and they're non-contractible loops, so they wind all the way around the system. And for now, let's say we do periodic boundary conditions. Yeah. Now, there's lots of densely packed configurations because essentially every row, these guys can march either to the right or the left. They have to move in lockstep, but there's lots of ways they can wiggle as you go down the system. In fact, there's an exponential number of such densely packed configurations. But once you've made a densely packed configuration like this, then there is no subsequent dynamics you can have. Yeah, because any subsequent loop fluctuations are going to create intersections, and intersections you are not allowed. Yeah, the only way you can get from this sort of state to any other constraint satisfying state is either to delete an entire loop or to put a kink in this entire pattern. But any of those things requires acting on order L degrees of freedom, where L is linear system size. And we only have k local perturbations at our disposal, so we can only make few body perturbations. Yeah? And you cannot rearrange order L spins at any finite order in perturbation theory if the only thing you have access to is k local perturbations. Yeah. So yes, Sal.
Oh, so is this some kind of maybe subsystem symmetry?
This is not any kind of subsystem symmetry. No.
Okay, thank you.
Sal.
I think I missed something. So at one point, the loops were like the domain walls, and they're always contractible. But now we're allowing ourselves to consider non-contractible loops.
So now we're doing periodic boundary conditions.
So
with periodic boundaries, we could have non-contractible domain walls.
That's fine, but I don't think you can excite a non-contractible domain wall individually with some operator.
That's right. Yeah. So then they would come in pairs. But you could make a pair of non-contractible domain walls if you
Okay.
wished.
Okay. So you always make sure you have like maybe some even system size. Okay.
Sure.
Good. I'm happy. Thank you.
Okay, but every state of this sort is an eigenstate of any dynamics, just because of the constraint structure here. And if the constraint is imposed exactly as a hard constraint, then these are exact eigenstates, true to infinite times. If you say that, okay, actually you're allowed to violate the constraint, it's just that constraint violations cost some large energy penalty, let's say J, yeah? Then, okay, constraint violations cost some large energy penalty J. You only have some small perturbation strength, maybe V at your disposal. But if you act with the perturbation J over V times, then maybe you can get back on energy shell. Yeah. So maybe there is a way to rearrange these states. It just requires going to very high order in perturbation theory. You have to go to order J over V in perturbation theory, and that'll give you a time scale which is exponential in J over V. Yeah. So this intuition can be formalized by the by now standard theory of prethermalization, and it gives you this time scale which is exponential in the perturbation strength. Yeah. So you could not get this at any. Right. I mean, it's non-analytic in perturbation strength. It's super polynomially long, finite, but exponential. Okay. Now, I was asked about if there's a subsystem symmetry here. There's not a subsystem symmetry. There is a higher form symmetry. Yeah. So you can actually think of these domain walls, red and blue, as symmetry charges of a higher form symmetry. In this case, it's a U1 one form symmetry. Yeah. And anytime you have a symmetry, I mean, your time evolution is always block diagonal in by symmetry quantum number, because time dynamics cannot change your symmetry quantum numbers. So really, you should be resolving your dynamics by the higher form symmetry. So you should take your big unitary time evolution matrix, you should block diagonalize it into symmetry sectors, and you should look at the evolution within each symmetry sector. And your sort of default assumption should be that if you have a one-form symmetry, then the dynamics should be magnetohydrodynamics. Yeah, because so magnetohydrodynamics is the dynamics of fluctuating loop-like variables. Leo.
Fine. So, two states which have no loop, a state that has no loops and a state that has contractible loops, those are in the same
correct
sector.
Correct.
So like what you drew here, the ones that survive are the non-contractible loops in your periodic boundary condition.
Yeah.
Okay, thank you. Unless there's some spaces not simply connected or something like that.
Correct. Yes.
Okay.
So for now, so what we can do is we can take the dynamic, the unitary matrix, and we can block diagonalize it, and each of these blocks can be labeled by quantum numbers of this one-form symmetry. And when you do this, you find that there's two sorts of symmetry blocks. So there's one set of symmetry block where the dynamics is ergodic, and it follows magnetohydrodynamics, which is our baseline assumption for a one-form symmetry. And there's another sort of symmetry block which consists entirely of these densely packed configurations. Yeah? So there is ergodicity breaking here, but it's all or nothing. There's some symmetry sectors which are ergodic, and there's other symmetry sectors which have no dynamics whatsoever, because they consist only of completely frozen configurations with no time dynamics. Yeah. So this is sort of very special. We'll see that in a little bit how you can get stuff which is not all or nothing. But in this very simplest model, there is ergodicity breaking with the sort of all or nothing character. And for now, the sort of interesting physics is also limited to periodic boundaries. Yeah, both this all or nothing character and the sort of limitation to periodic boundaries are just artifacts of this very special model. So now, yeah.
Suppose if you put up that image of the to the next one.
Yeah.
One more. Yeah, that one. So like if I skip one of the, let's say one of the blue lines.
Correct.
Then it seems like I'll have local dynamics, but it'll still be non-ergodic.
In
that I can't
right. So
really
if you
move
delete even a single one of these lines in this model,
immediately,
it becomes immediately ergodic.
So how do I see that? Why isn't it like I'm still constrained by all the other guys? I can just kind of rattle around in a cage.
But now you have room to wiggle, so you lose the sort of dense packing, jamming characteristics. So then, the ones, if you deleted, let's say, this blue line, then the red loops immediately around can wiggle a little bit, right? And then that creates space for the next ones over to wiggle, and so on.
Yeah. I see. So it eventually kind of relaxes itself.
Yes.
Thank you.
And yeah, I mean, if you really had a thermodynamically large system and you just deleted one line, right, then it would start to melt from that line outwards. So if you went sufficiently far away from that line, you'd have to wait a very long time for it to melt. But if you removed, say, a finite density of these lines, then you just get a finite time scale. Yeah, in the back. No, yeah, so in this model, it is, well, no, it's not broken, it's just there.
It's just there. I mean, so it's not broken. That's what you mean?
Yes. Yeah.
Oh, okay, thank you.
Yeah. Okay, so now let me tell you about how to generalize this construction. Yeah, this CZP model seems very special. Actually, it's part of a much broader family of models. And when you generalize it, you find that you get sort of ergodicity breaking much more broadly without this all or nothing character and without this limitation to periodic boundaries. And sort of step one in doing that is, let's stick to square lattice or maybe cubic lattice, but instead of having spin 1/2 variables, we'll move to m state clock spins, where m is 2 or more. And if m is 2, then we're back to exactly the CZP model I was just telling you about. But if we make m 3-state clock spins or 4-state, 5-state, then we get something new. So if we go to clock spins, then we have more species of domain walls, basically. So let's say we had 3-state clock spins. We would have 3 kinds of domain walls. Let me call those red, green, and blue. You can still define these sort of one-form symmetry charges. The Hilbert space still consists of closed loops, which are these different species of domain walls with a non-intersection constraint. The constrained subspace is still an honest 2D subspace. It's exponential in system volume, so it's big enough to accommodate a non-zero entropy density. And so we can meaningfully talk about dynamics and thermalization or lack thereof in this constrained subspace. I'll remind you the Hilbert space now consists of m species of closed loops, where m is now 3 or more to be sort of different to what we had before. And with the constraint that loops of different colors cannot intersect, but subject to the constraint that loops of different colors cannot intersect, they could fluctuate any which way. Yeah. Now let's consider some state. It has some collection of loops. Some of those loops are contractible. Some of those loops might be non-contractible. I don't have to do periodic boundaries now. I could even do open boundaries, and maybe the loops are allowed to terminate on certain boundaries, but not on others. Yeah, so you could do sort of rough and smooth boundaries. But you have some sort of, and by non-contractible loop, it could either be something which goes all the way around periodic boundaries or something which terminates on the actual physical boundary if I was doing open boundaries. So let me consider some state of this sort that satisfies the constraint. And now let me just march from left to right across the system. And every time I encounter a non-contractible loop, I will record the color. Yeah. So for this particular state, the color what I would get is I would march along from left to right. I would record here green, then I would record red, and then I would stop. Yeah. And this record, this sort of ordered sequence of non-contractible loops of non-repeating color, I can call this a word if you wish. Yeah. So each non-contractible loop is a letter in a certain color. and the ordered sequence of letters is a word, and this word is a topological invariant. Yeah? Because there's no way to change this word without either pushing one non-contractible loop through another or creating or destroying a non-contractible loop. And either of those things requires acting on order L degrees of freedom, and we can't do that at any finite order in perturbation theory. Yeah? So now we have topological invariance of our dynamics. We still have these one-form symmetries, but now these topological invariants can't change under any local constraint satisfying dynamics. And now if we just do some basic counting, there's polynomially many symmetry sectors. Yeah, so the number of possible one-form symmetry charges is polynomial in system size. But there's exponentially many topological invariants. So there must be ergodicity breaking. I can't possibly explore all states with the same symmetry quantum numbers. Yeah? And furthermore, you can show that there are finite size motifs you can introduce, which are neutral from the point of view of symmetry charge, but which have a non-trivial word associated to them. Yeah? And so, in fact, now you see that ergodicity breaking is generic in every one-form symmetry sector. Yeah, like your unitary time evolution matrix is not just a random matrix in that symmetry sector, which is what you would expect for an ergodic model. Instead, it consists of exponentially many subblocks, with each subblock being labeled by its own topologically invariant word.
Yeah? So what happens if your Hamiltonian also non-local? What happens if you have the non-local Hamiltonian? Is this also?
Yeah. So, it depends what you mean by a non-local Hamiltonian. If it's just spatially non-local, it doesn't matter, right? Because just allowing yourself to perturb with something that's spatially non-local doesn't allow you to change topological invariance. Now, if by non-local you mean there are terms which are truly global, meaning they act on every single sort of degree of, not even k-local, right? They act on every spin at once. Then you've got nothing, right? But yeah, so you need at least k-locality, or at least the sort of information theoretic notion of locality, but you don't need geometric locality. Okay. And yeah, this can generalize to higher dimensions, and I'll come back to that in a bit. So far, I was working on square and cubic lattices. That's not essential. You can actually, so I was working on square and cubic lattices, and I was using states which are essentially describable as loop soups of some sort. Yes?
Thank you. So in these models, which are now no longer all or nothing, how would you diagnose the ergodicity breaking? Like, could you diagnose it in local observables? Or is it now possible that sort of only if you consider non-local observables, you see in the dynamics that it's actually non-ergodic?
Yeah. Yeah, I don't know. You might need to do some decoding, right? So given a state, if you measured, so you could measure the kind of colors you encounter along a cut, but that's not really a local observable, or, it's some sort of extensive set of local observables on which you would then need to do some decoding. Now, can you see it in some purely local observable without decoding? Maybe, but I don't know how.
Thank you.
Okay, so thus far I was working on square and cubic lattices with states that were describable as loop soups. Now we'll come to something more general, which will actually also give an affirmative answer to that question. Yeah. So now suppose we sort of generalize the set of symmetries we're considering from U1, one form or whatever, to arbitrary symmetries, and suppose we generalize to arbitrary lattices. Yeah? Is there a way to do this? In fact, there is a way. And the formalism to use here is the formalism of what's called the group word problem. So the setup here is you consider a Hilbert space where the on-site Hilbert space is spanned by a set of characters, each character representing a group element. If you're in 1D, then your many-body Hilbert space consists of strings of characters, which you can call words. If you're in 2D, this lifts to a sort of crossword puzzle and so on. And the dynamics is implemented by local equivalence relations between strings of characters. And then you can say that the problem is really one of classifying words into equivalence classes under this dynamics. Yeah. So you have different strings of characters. Some of them can be turned into one another. under these sort of local equivalence relations. And the value of this is actually there's a sort of well-developed technology and body of results in complexity theory for this problem, which can be sort of borrowed and leveraged to prove stuff. So you can do this and sort of apply this machinery of the group word problem to formulate this on an arbitrary lattice. And the way to do it is you set it up in where you have an arbitrary lattice. The on-site Hilbert space is a set of characters, which are group elements. And the basic requirement is that the word read around any elementary plaquette should be reducible to the identity under some sequence of local equivalence relations. So this is what we call the flatness condition. And this generalizes our construction to arbitrary lattices, arbitrary dimensions. Now, you don't really have to work with loop soups anymore. In 2D, there's a much broader family of models which look like string nets with the sort of loop soups I was talking about before as a special case. In 3D, you get models which look more like sponges, where you have different membranes which can sort of merge or demerge. And all of these models have sort of emergent higher form symmetries and pre-thermal topological stability. There's also lattice-specific phenomena. So you could imagine, for instance, introducing lattice defects. And if you introduce lattice defects, then you'll get sort of local changes in the sort of allowed equivalence relations. And now lattice defects can actually sort of trap single charges, which can't move. And that could be a sort of diagnostic for what Johannes was asking about sort of local probes of ergodicity breaking in these generalized sort of string net and sponge setups. And yeah, in fact, you're not even limited to sort of 2D, 3D lattices. You can actually generalize this to arbitrary graphs without even spatial locality, except once you go to arbitrary graphs without spatial locality, then like you don't really have a notion of topological robustness anymore. So like maybe to avoid throwing out the baby with the bathwater, we stick to lattices in some finite number of dimensions where you have a notion of geometric locality, and then you can write down models with sort of topologically robust ergodicity breaking. But in principle, you could also generalize these models to arbitrary graphs. Okay. So I've told you about how we could sort of massively generalize these results on the CZP model. First, from loop soups to sort of string nets and sponges, and also from states in 2 dimensions to states in arbitrary number of dimensions, and in principle also in arbitrary graphs, arbitrary boundary conditions, blah, blah, blah. And this is sort of a very general phenomenon, and the CZP model is just the first example, but like there's this broad family of ways to do it. And the basic requirement is we need to introduce this single constraint, originally the CZP constraint, now this flatness constraint, that the word read around any elementary plaquette is equal to the identity. Yes?
Could you probably maybe comment more about arbitrary lattices? Because what you discussed before was for square lattice, but for example, if I will take triangular lattice, I think you shouldn't you change essentially your model for that case?
Yeah. So there certainly are lattice-related effects. So if you try to define exactly the model I had before on the triangular lattice, you just can't do it. So there's some compatibility constraint between what group you want to use to define your Hilbert space and what lattice you're on, and therefore what equivalence relations you can impose. But what you could do, for instance, on triangular lattice is you could have 3 colors A, B, and C with the equivalence condition that A, B, C is identity, and that would give you a different set of allowed states on the triangular lattice. Okay. So thus far there was a single flatness constraint, and this gave ergodicity breaking that was robust out to exponentially long timescales. Yes. Yes, that's a very good question. So given the level at which I was discussing this thus far, you would think that there should be a continuum version of this. I've certainly been thinking sort of off and on about how to really formulate this crisply in the continuum. So there's a stumbling block, which at least thus far I haven't figured out a way around, which is that if you try to do these pre-thermal bounds in the continuum, your energy density is unbounded above. And that's a sort of that's a problem for trying to establish any sort of pre-thermal bounds. Like whether it's a purely technical problem, which can somehow be resolved, or whether it's a fundamental problem, I don't know. Okay, so no, so far, yeah, pre-thermal bounds, you get sort of exponentially long timescales. Can you get timescales which are truly infinite instead of merely exponentially long? So that's what the last part of my talk will be about. Our objective is we'd like to get truly infinite timescales, and we believe that maybe the way to do this is to use this notion of exact emergent higher form symmetries from Pace and Wen. Now, Sal is right here in the audience. I'll show you a model which we call the rainbow loop soup, which we believe in 2 dimensions gives exact, meaning infinite time ergodicity breaking, only at 0 temperature. Yeah. So exact ergodicity breaking at 0 temperature is not so ergodic, is not so remarkable. Kim and Ha showed how to get this in Fracton models 10 years ago. Except Kim and Ha are working in 3 dimensions. Now we think we can get the same thing in 2 dimensions. So it's a small win, right? We've gone from 3D to 2D. But then I'll show you a model which we call the rainbow membrane soup, which is much more dramatic. And this, we believe, gives exact ergodicity breaking even when coupled to a non-zero temperature heat bath, which is not something you can get in MBL or actually any other model that I know of. Yeah. So this is something really new. I will caution that the stuff I'm talking about in this last part of the talk is stuff that, well, I think it's true, I think it's plausible, but our arguments are certainly not rigorous. Yeah, so this is certainly something where a proof is needed. And if you have ideas as to how to prove this stuff, now let's talk about it in the next coffee break. All right, so let's start with the rainbow loop soup. As we've been doing before, let's work with a Hilbert space, which is m greater than 2 colors of loops plus vacuum with loop intersections energetically penalized. As before, we can label states by topologically invariant words. And let's say that the length of the word is lambda, yeah? Where lambda can be no larger than linear system size. And now let's tune to a Rokhsar Kivelson point so that so you have some, your Hilbert space breaks up into sectors. Each sector is labeled by its own topologically invariant word. But there's lots of different loop configurations with the same topologically invariant word. So now let's tune the Hamiltonian to a point where the ground state in that sector, the lowest energy state, is an equal weight superposition of all states with the same topologically invariant word. Yeah. If you perturb, let's add a perturbation that favors sectors with short labels so that the word that's topologically invariant is short. And now some numerics suggest that the energy density of this ground state depends only on the length of the word measured in units of system size. Yeah? And this is plausible because this basically sets the density of non-contractible loops. Yeah? So it's equal weight superposition over all contractible loop configurations, basically. And it depends only on the density of non-contractible loops. And now our claim is that all short label ground states are exact steady states in the thermodynamic limit. So there's a formal way to argue this, which is essentially to say that, look, the danger is loop intersection. So the way you change this topologically invariant word is you create a loop intersection and you sweep it across the system. Yeah? Now, when you do that, the loop intersections violate this emergent higher form symmetry. And Pace and Wen tell us that in 2 dimensions, if you have an emergent higher form symmetry, it must be exact. So you can't have these guys. Yeah? There's also an intuitive argument, which is to say that, one sort of danger is that you could have false vacuum decay. So you set up a state with some topological invariant, but it really represents a false vacuum. That's the true, that's the apparent ground state with a given topologically invariant word, but it's not the true ground state. And so the system can decay to the true ground state by nucleating a bubble, and then that bubble sort of grows and covers the entire system. But bubble nucleation relies on the fact that now you're working in a false vacuum state, which is at non-zero energy density. So you can go to a lower energy density vacuum state. Yeah? And here we don't have that. Here we're working with a false vacuum maybe, but it's a false vacuum with locally minimal energy density. So we're not really winning by doing bubble nucleation. But so far, this is only working at 0 temperature. Because Sal tells us that this in 2D, it doesn't work at non-zero temperatures. So can we get something at non-zero temperature? And intuitively, the problem at non-zero temperature is, okay, these loop intersections, they cost energy, but they only cost finite energy. So if you're at non-zero temperature, coupled to some heat bath, you just borrow the energy from the heat bath, and then relaxation is some Arrhenius activated process. Yeah? Exponentially slow in temperature, but still finite time scale. Now, if we go to 3D, now you have membranes. So you have two-form symmetries. Membranes are the symmetry charges of the two-form symmetry, and membrane intersections cost finite energy per unit length. Yeah? And now the way you would change, so everything else works much the same, except now we believe that this should remain robust to non-zero temperature. Formally, this is because emergent two-form symmetries can be exact even at non-zero temperature, and the membrane intersections violate the emergent two-form symmetry. The intuitive argument is that in order to change the topologically invariant word, you need to basically push one membrane through another, which means you need to create a membrane intersection, and you need to grow it across the entire system. But that has a divergent energy barrier associated to it, because the membrane intersections cost finite energy per unit length, and the length is linear system size. And your non-zero temperature heat bath, it can certainly nucleate small membrane intersections, but it can't supply the energy for this to get over this divergent energy barrier. So we think that these topologically invariant words in this 3D membrane soup should be not only pre-thermally stable, but actually completely stable to timescales which are not just exponentially long, but actually truly infinite.
So what happened in the case of 3D, but we only have one form symmetry rather than two form?
Yeah, so if you were in 3D and you had only one form symmetry, then your Hilbert space would be loops rather than membranes. So you could still have knots associated to loops. And you could, if the constraint that loop intersections were not allowed, if that was a hard constraint, then you would still have ergodicity breaking, which would be labeled now by knot invariance. But there's nothing robust about this, right? Because a sort of second order in perturbation theory, you create a constraint violating state and then you go through it. So you don't have any robustness, but if you're willing to impose the constraint as a hard constraint, then then you still got something, but that's a little too permissive for my taste.
So basically, the crossing, if only satisfied in terms of perturbation, then you say that it's not a problem. But if it's the hard constraint, then it could be.
Yes.
Okay.
With a hard constraint, you've still got ergodicity breaking. But the moment you relax away from a hard constraint, you've got no robustness. Okay. So we believe that notions of exact emergence allow us to get truly infinite timescales, even at non-zero temperature, even when coupled to a heat bath in 3 dimensions. We've sort of excluded the known instabilities, which sort of restore ergodicity. What we haven't excluded are unknown unknowns, right? So if there's some instability channel which we don't know of, then all the known things that destabilize, like MBL or Hilbert space shattering, those don't seem to be in play here. But in sort of Rumsfeldian terms, unknown unknowns we don't know about. So that I think a proof is still very much required, but at least as of now, I don't know how to do it. But if you have ideas, let's talk about it. All right, so now let's wrap up. I've shown you a new route to ergodicity breaking with unprecedented topological stability, no longer requires geometric locality. It's robust to geometrically non-local perturbations. We can prove ergodicity breaking in a very wide class of models. We conjecture that we can even get exact ergodicity breaking. This needs to be proven. And also maybe just to close, what I've really shown, it is ergodicity breaking, but what it gives us is really topologically robust classical memories, because you have these patterns, and you can perturb, and the perturbations don't change, let's say, these topologically invariant words, but you could always perturb with, say, diagonal perturbations, which would change the phase. So here the phase information is not protected. And whether there's a way to get sort of topologically robust quantum memories where the phase information is also protected and in dimensions 3 or less, that's a very interesting topic, but I don't have an answer to it yet. So maybe that's some other talk sometime in the future. Okay, so that's it.
Maybe question?
Thank you. Oh, sorry. If I'm remembering correctly, I think in the first part you said this is a U1 one-form symmetry. Is it correct? You said this is a U1 one-form symmetry.
Yes.
Right? So how can I see this is U1?
How can you see it's U1? Yeah, okay. So you need a slightly better duality than the one I showed you. but really you should think of these loops as being oriented loops. And the U1 is just count, and instead of having blue and red loops, instead you just say that you have two species of oriented loops. And then the U1 charge is just counting how many oriented loops you've crossed, but like sort of signed, right? Sort of positive sign minus negative sign. Yeah.
Okay, thank you for the nice talk. So this ergodicity breaking, does it, like the time scales of pre-thermalization, does it depend on initial conditions? Or there are some regions of initial conditions where you start with, then only you see this time scales?
So the question, if I understood correctly, was that the pre-thermal timescale, does it depend on initial condition? Was that it?
Yes.
Okay. Yeah, so the bound that I showed you, which is sort of exponential in perturbation strength, that bound is a worst case bound. So you pick an initial condition, which is like essentially at infinite temperature, in the constrained subspace, and then that's the bound you get. Your timescale could certainly be longer than that bound. Yeah, like if you picked some initial condition which was very favorable to you, but it couldn't be worse.
All right, let's move on. Let's take the speaker one more time.